X e to the y with respect to x.
Should be e to the power y.
E to the y. Good. So you got it. Very good. Well, what if it was y? That's easy. That's easy. Yes. So I'm going to go with that. The partial with respect to y would be x e to the y. Right? That's the constant in front. You're just taking the derivative with respect to y. So, hey, one more. What if it was like x cosine y? Because I think there was one of those. What was that? All right. It should be similar, but cosines and e to the x's and e to the y is a little different. What's that? 1, 0. All right, what's this?
That's cosine y.
Good job, cosine y. Now what's r? Y? 0, 1, and
Negative sine.
Negative sine of y times
X,
that.
X.
There you go. And notice you said negative. You got it. I mean, I just don't think anything could stump you unless somehow they had a hidden product rule where they did this stuff. Your surface z was like x e to the xy. And then when you had to do the partial respect to x, you go, oh, I need product rule, if that ever emerges. But you got it. You got it. Very good. Hey, there's something we got to study right now. It's surfaces that are totally. I put this folder here, Bush. Just like this, horizontal or parallel to the xy plane, or surfaces that are totally vertical like this. See, that surface wasn't. You see it curving? Something interesting happens on these types of surfaces, so we're going to look at that now. I'm talking about surfaces that are totally flat, which we could say a horizontal plane parallel to the xy plane, or something that's totally vertical. And it doesn't have to be a rectangle, it could just be a circle or a disc. So on that note, everyone, here's the first thing I'm going to have you do. This is you want to work along, you look at number 10. Here's the vector field. XY, 3C. Upward orientation. So it's oriented upward. And this is what they say about the surface. So I'm going to write this down. The surface S is a horizontal. Plane Z equals 4. Consisting only a disc. I'll put parentheses with x squared plus y squared less than or equal to 4. And it has upward orientation. So you want to draw this now just a disc like this at z equals 4. That's our surface, right? That's all we got. And the normal vectors will go upward. So what would that look like? Z-axis, can we draw that? 1, 2, 3, 4. There's a circle. Anybody know the radius? Can I write this?
2.
Excellent. X squared plus y squared equals r squared. They put the less than or equal to because we're talking about the disk. That would be r squared. So the radius of that disk is 2. So everyone got that? But all the normal vectors will go upward. All right, up. I'm going to make a note, everyone. That radius equals 2. This is at z equal 4, right? Here's the z-axis, positive z-axis. You got it. Well, I hope you find this problem easier than the last one. The challenge is, how the heck do you parameterize it? How do we parameterize this? And in the end, you're going to find this probably a lot easier than the last surface that we just did. I got to parameterize that surface. You want to project it right onto the xy plane. Is that okay with that? I agree. So I'm gonna think, parameterize this. That's the biggest challenge I win because I need this. So I can do that f of r or u comma all that. So I'm gonna get this. I'm using x and y because I'm projecting downward. Now if the disk was like this, maybe I could project it onto the yz point. Nice later when you get into the y-axis, there's the x-axis. So, can you help me with this? Ready? These are my only two letters. I can't have any z's in here. X equals x, y equals y. What's this?
4.
There you go. Look, isn't that interesting look? I just parameterized that surface. Now it would go forever. You can think of a flat plane. But how do we restrict it to just a disk? That's going to happen right here. Students ask questions about that. They're like, really? Isn't that just going to go forever? Z equals 4? I go, yeah, certainly. But when we do the double integral, we're going to restrict it right there to a disk. You follow me? And you might even do polar coordinates if you want. True? But I don't know if you're going to use polar coordinates. You might have an easier way. Because this should make the problem a lot easier if it's totally horizontal. Okay, so radius 2, let's start it out. What's RF? 1, 0, what's that? Oh man, this moves fast. What's the next one?
0, 1, 0.
This is what I'm talking about. This should be a lot easier. This should be an interesting normal vector that you are going to look at and go, yep, that makes sense. What do you get? What is Rx cross Ry? I'll let you do the cross product.
0, 0, 0.
0 times 0. Negative 0 times 0. That's not a 0 though. Does this make sense? It's a unit vector. A diagonal unit vector with a length of 1, right? Pointed upward. That is upward, right? Hey, can you simply tell me what if they said downward orientation? I would have just what?
Negative.
Yeah, negative 0, negative 0, negative 1, 0, 0, negative 1. Oh, that would point it downward. We get it. They said it oriented upward. So that's why on here they all are. They're all unit vectors. So hey, does that always happen on these flat surfaces? Yes. So you might rush to it and just go, oh, they're just going to be 0, 0, 1s. But if you have any bending like this, a paraboloid, or what do we have earlier? We had the cylinder, the parabolic cylinder, and then the surface bends, then we're going to get something different. Cool. And you got it. So, let's try to find out what we get. Let's get the flux across that, and what do we get? Boop, boop. What's F composed of? R, U, V. We're doing R of X and Y. And we got to multiply, do the dot product with Rx cross R. dA. I'm going to keep writing dA because you might find a quicker way to do this problem. So what's this? X, Y, 3Z. What gets substituted? Because I'm thinking maybe I'll project this right onto the XY plane. We're going to do everything in terms of that. So right here, hold up. What do I substitute for that Z?
4.
Yep, and you go look. So that's what I mean. That's where you can get lost. Because maybe you didn't even parameterize it. So you're like, what would I substitute for the Z? And you look and you go, oh, it's the 4. That's the Z component of my surface. Z was always 4. It was a constant 4. This is going where? Now you have the double integral of, what's x times 0 plus y times 0 plus 3 times I gotta put a 4 there, right? So what's x, y, 12 dot 0, 0, 1? I hope you find this problem easier than the last one.
Just 12.
Now do you have a fast shortcut for doing double integrals of constants? Because I can put the 12 out here. That means this is a 1. What's double integral of 1 find? Area. So if you want to bypass polar coordinates, which you all would do a great job with, use R, write R d theta, like the pirate. Isn't this just 12 times the area of the disk? Yeah, so that's what I'm gonna do. What do you get? What's the disk radius? Pi radius squared. I'm not even doing calculus, just taking the area of this pi times 2 squared. You don't have to do this, by the way. I have students in the past, and they go, no, I just did double integral, thank you very much. Polar coordinates. What is that, 48 pi? 48 pi. Everyone okay with that? Got it. 48 pi. There's two more things we're going to do. And there's a reason behind this. I'm going with something. I'm going somewhere with all this. You just found a flux across that. And what was the flux? 48 pi. So I got to keep that across that top disk. It was, the flux was how much? 48 pi. Well now, can you get the flux across this next surface? And you'll see it, and there's an image here when it's a paraboloid. It's a paraboloid that opens up like this. I'll put it right here. Can you get the flux across this surface? But that means that top's not there. So when I'm going to remove the top now, is everyone okay with that? Because that's just an open surface. They call that an open surface. Like that's not closed up. I want the flux across this surface. They gave the equation. So I'll erase everything. So I got to erase everything. Get this. What is the surface? So here comes part 2. Same vector field though. So I got to get rid of all this math. I'll leave that though. Same vector field. And this time, it's the paraboloid. Z equals x squared plus y squared. And the orientation is downward. So your normal vectors are going to be oriented downward. So just to remind you, can you go into this image and maybe just stick some like vectors like this so we don't forget that we got to make sure it's going to be down. But do you notice the top's missing? If we're talking about the surface, where's the surface? It's all that lateral portion. It's all the lateral portion. So all the normal vectors are coming off here. You go, what about the top? No, this is not. So let me mention, this is an open surface. A closed surface, you know what a closed surface is? Think of like a sphere. That's a closed surface. Right? A closed surface, can I point to that? We're talking about like all this and the top, everything all closed up. Where this, that's an open surface, so nothing coming off the top, so don't put anything off here. Great? So we're just getting this, all this flux across here. Oriented down. So, can you parameterize that surface? You want to use x and y? What would you get? X equals x, y equals y, and what's the last component?
Z.
X squared plus y squared. Now what's our 1, 0, 2x? Everyone okay with that? What's our y? 0, 1, and a 2y? What's the cross product? Rx cross ry. Because I keep doing Rx cross ry, I'm going to continue doing it. Unless we need to change it. What's the first component? 0 minus 2x. Middle component, negative 2y minus 0. So what's this last component? So help me out. What should I use for my normal vector? You're the best. So what I'm going to do, we're going to use this normal vector. The one that goes in the opposite direction. 2x, 2y, negative 1. That's the secret to section 16.7. As long as you stay with the orientation, that means what? Downward. See, that means down. All the normal vectors will get pointed downward. Will they all look like this? Nah, some are going to look like that. Some are going to look like that. Coming off here, right? Look, they can be bent because it can be perpendicular at that, at a tangent plane. Let's roll with it. Ready? Whoop, whoop. what's this? X, Y, 3z. And I'm dotting it with what? 2x, 2y, -1. dA. But what goes right here?
X squared plus y squared.
Way to go. So this gets substituted there. But the x stays the x, the y stays the y. So now what do I have? X, y, x squared plus y squared. Dot product with 2x, 2y, and a -1.
Shouldn't it be 3x squared plus 3y squared?
Uh-oh, did I mess up? Yeah, you're the best. Thank you. He says there's a 3 there. So 3 times, I'll get the parentheses there, or you can substitute it right away. 3x squared plus 3y squared. Very good. And I'm still putting dA, right? I'm still going to write dA. Eventually I'll put dy dx or dx dy or go polar. What is that dot product? X times 2x is
2x squared.
2y times y
2y squared.
minus
3x squared.
3x squared minus
3y squared.
yeah. Any like terms in there?
X squared y squared.
That's 2x squared minus 3x squared.
Negative x squared.
2y squared minus 3y squared. Want to factor out the negative? Man, you all are awesome. Seriously, really good. Now, we have a decision to make. Where am I projecting this? Look at your surface. When we think about the projection, it's like, oh, the widest region ever encountered by that surface is a disk. So my projection will project this onto the xy plane. It's the widest, but where was it the widest? Up at z equals 4. So when you're going to help me figure out what would be that disk. It's a disk where this 4 is equal to that equation, right? That's the disk, that's our projection, because it was the widest portion ever encountered. So I'm going to go right here, and this is our projection right here. It's x squared plus y squared less than or equal to 4. Because I set this surface equal to the 4. That would be my disk. What is the radius of that disk? Because I know we're going to want to go polar, aren't we? Put a picture of a disk. There's your disk. But the radius is 2, but we're going to go what? Go polar. You got to love polar, because look. I have this much room to write. I know we can do it. I know we can do it right in here, everyone. There's enough room. I'm going to go polar. So what do you get? Negative. R squared. What's automatic? R. RD data. There it is. 0 to 2 pi. And the radius? 0 to 2. Does everyone know why I used a radius of 2? I had to think where the surface was equal to 4. Okay. So what is this integral? What's the integral in r cubed? Okay, negative 2 pi. What's the integral in r cubed? Are the 4 over 4 from 0 to 2? What's that final answer? It's negative 2 pi times all that. Oh, I'm getting a negative value. Negative 8 pi. Negative 8 pi. This is the flux across the what? The lateral portion of the parabola. So I'm going to include that here in our notes. Flux across the paraboloid surface, without the top, right, is negative 8 pi. And I'll wait till everyone copies this. You'll see where I'm going with the next question. And we're about to wrap it up. The next thing's going to be easier when I'm not going to have to tilt this whole board. I think you're going to know logically what to do. So when we found the flux across that top disk that was there originally, true? That was easy. We got the flux across this bottom portion. Then what would be the total flux if I made this a closed surface? So that's part C. Wait, some people are copying. I'm going to wait till you get all this. Flux across the top disk was 48 pi. The flux across that paraboloid, we're getting negative 8 pi, right? oriented downward. Now, what would be the flux across this included with this? And I say oriented outward. That's my word. Can I erase them? You sure? All right, I'm going to erase. So flux across this surface with a what? Close up this. This is now a closed surface. Aha. And my wording, I say oriented outward. What does outward mean? Well, we know. Just go outward everywhere. Up here, up here, up here. We get it. What would you do with those two numbers over there?
Add them.
Just add them together. That's the idea. So this problem's easy. I don't have to do all that. Oriented outward. It was the what? Plus.
Negative 8.
And what do you get? 45. The reason I did this, that took a little while, didn't it? We only have 2 sections remaining after this. Only 2. One of them is dedicated to closed surfaces because they're kind of a pain. I want to talk about that. Like, you had to do this separately, then you had to do this. What if it had 3 different portions to it? Oh my goodness, Ellen, can you think of a cube? How many sides to a cube? 6 sides. So you're going to get 6 fluxes? Well, yeah, but they all be flat or horizontal. That wouldn't be too bad, right? But still, it's a cool theorem. It's called Gauss's divergence theorem, and it's a one-shot, give me the total flux across, but it only deals with closed surfaces. So when you get to that, we should go back to this problem, and it should take us like 5 seconds to do. Cool? Hey, right before you leave, can you tell me if you got a thing that's on the side like this, how you can get that flux? That'll be the last thing. Like, what if it was like, we did one like this, it was upward, but what if it was like, you know, on the x-axis or something? That's the last one. I'll just compute with you. Let me add something like this. I'll draw it. And when it's over here on the x-axis, and let's just say it's like right here. How do you want to do it at x equal to 3? So here's x equal to 3. Get this junk out of the way. Let's make up a different vector field. How about x? How about 4x, 5y, 6z? That's our vector field. Can you give me the flux across this surface right there? But I'm going to tell you how big that square is, Ellen. That's a square, and it's a 2 by 2 square. So what that would mean, and when you want me to list this out, I'm saying for the y's, I want you to go from -1 to 1 for y, and then for z, go from -1 to 1. That's what I'm saying about that square right there. But the square is, what's its dimensions?
2 by 2.
2 by 2. So maybe in my drawing up here, and with that y-axis, you can go a little bit further. The z-axis goes up, I can go downward, I can extend this. But I'm saying go from -1, z equals 1, z equals -1, and go from -1 to 1 there. But it may look weird because it's over here. But I'll try to make these tick marks a little bit bigger so you can actually kind of see how it just got. Here's the negative z-axis. Okay. But this is where I got to be very clear about the orientation. So how about oriented in the positive, in the direction of the positive x-axis? Oriented in the direction of the positive x-axis. And when can you find the flux across that x? Which way are they going? So let's put some arrows on here. Oh, they're going this way. Does anybody already know what normal vector we use? It's going to be a unit vector because when that surface is like this, boom, and it's a unit vector that has to go that way. which is what? He already knows this. So that normal vector is going to be 1, 0, 0. And he hasn't done any of the math. When we parameterize this surface to get to the cross product, he's saying that right there will be 1, 0, 0. Question, what if they said oriented towards the negative x-axis? Then I would have used negative 1, 0, 0. Does that make sense? Cool. But you want to see this coming down? If you're like, I'm not seeing how he knew that. Well, let's play with it. If you parameterize that surface, well, I can't use x and y. What would be a good way to project this? Can you see it? Like, take this and throw it that way. Project it onto what plane? The YZ plane. So guess what I would use? I would use y and z. Does this make sense? I'm parameterizing that surface right there. But it's going to be easy. Y equals y. Z equals z. But what the heck is x? You remember when I told you? This was located where? At 3. It's a constant 3, so what goes here? And that's the parameterization of that surface right there. Yeah, but it's only a square. We'll deal with that in a double integral. So now, check it out. What's Ry? 0, 1, 0. What's RZ? 0, 0, and a 1. And what's the cross product? Ry cross RZ. And we get 0, 0, 1, we're good. If it's 0, 0, negative 1, we'll change it over. What do you get? Nope, there's the 1 we thought we'd get. That's a 0, not a 0, right? Should wipe out this here. This times this one is this times this. There it is. That's what he knew that from before. So very good. I'll put that here, and here comes the flux of F across the surface. We call it a surface integral. F of R composed of Y and Z dot Ry cross RZ. dA. So 1, 0, 0. This should go quick. And then I'll just do dy dz. No big deal. Negative 1 to 1. Negative 1 to 1. See, that's where I'm going to do my limits of integration. Because they said this, right? So I'm going to build that up right there. What goes here, though? I hope you find this real easy. There's a dot product. Let me go back. Where was that? I made it up. I called it what? 4x, 5y, 6z. So 4x, 5y, 6z. But what has to replace? Because it can only be y's and z's. So what gets substituted for that x?
3.
That x gets substituted by that number, or what you saw right there. So that's what I mean. So you know what to substitute there. So what's 4 times 3?
12.
Right again. Negative 1 to 1. Negative 1 to 1. So when you're doing fluxes across flat surfaces that are horizontal or vertical, you should notice that the mathematics should come out really, really simple. That's what I want you to discover. What do you get out of this?
12. dA.
Now, has anybody got a fast way to do this integral? So he goes negative 1 to 1, negative 1 to 1. This becomes a 12 dy dz. I can take out the 12 and multiply the area of the what? The square. Well, what's the 2 by 2 square?
4.
12 times 2 by 2. 4 times 12 is?
48.
48. That's the flux across that side. And again, what if it was oriented the other way towards the negative x-axis? This would have became negative 48 because we would have made this a what? Negative 1. Hey, thanks. I just want to make sure you were comfortable. Like, not everything gets projected onto the xy plane, right? Sometimes you're going to project it one way or the other. Super job. Hey, you're going to love that last section. We can do that tomorrow with these normal vectors for the closed surfaces. That's the best part. And then we do Stokes here. It's only 2 sections left. Have a great day. I was going to pass that out.